Just getting set up here, 1 second. All right, should be good to go. Just move this out of the way. All right, so today I'm just going to be doing a brief review and a brief overview of Econ 257D2. I also had the same professor as you all, so a lot of the notes and the problems and the walkthroughs I kind of give you will be comparable to the previous exams you've seen, and hopefully, of course, the new one as well. Just as a piece of advice to start everyone off, I remember when I took the class, a lot of the old exams had the exact same problems as the most recent one. What he did was just change around the numbers and kind of mess around with some of the logic, I guess, as well. So honestly, when I studied, I would recommend that you just go back, do every single problem on the previous exams, on the problem sets a few times over, make sure you actually can do them correctly and make sure that you actually understand them. And if you can do that, quite frankly, you're in a great position to get an A on the final exam here. But without further ado, I'm going to walk you through some of the typical problems that we'll see and kind of give you an overview of the entire class. At least when I took it, first thing we covered was Bayes' rule, which is of course incredibly simple. So if anyone's taken some previous stats classes, you should be pretty good set for the probability problems that you're going to see here. But it does kind of relate it to utility functions and some other things as well. So typically you'll see a problem along the lines of this, and I'm going to kind of walk you through step by step how you would go about completing it. So we've got our utility function. So u of x is going to be x to the 1/2. And then the initial wealth is going to be x naught. So that's going to be 100. And then he's going to ask you to calculate the value of the share. And we kind of have to figure out, I guess, the logic behind the problem and how we're going to plug the numbers into the formula. So, we're looking at the share value of 300. If the company is strong, share value is going to be 0 if the company is not strong. And you can set up the terms or the, I guess, probability strong, however you want. But basically, if we start with x naught plus t, and again, that's going to be the initial wealth plus the payoff that we could possibly produce, and we're going to assign a probability to that. And you're looking to sell, you can calculate the expected utility of holding t, and then set this equal to the utility of selling t and receiving p. So we'll set it up something like this. Our expected utility of holding is going to be 1/2, again, because the probability up here is going to be 0.5. 1/2 the utility, or whatever the individual we're evaluating is utility, is 400. And then of course we add that to, again, 1/2 utility of 100 to try to kind of come up with the, I guess, expected utility from the gamble that we're given. So that ends up being, you could work through the algebra, you end up getting 15 there. Utility of selling, on the other hand, is going to be u of 100 plus p. Plug that into the formula that he gives you in the problem that I gave you here. So that's going to be up here. And you're going to get 100 plus p to the 1/2 power. At this point, we're just solving for p, and this is going to be the lowest price that we would sell the share t for. And you can walk through the algebra like this. And that price is ultimately going to be $125. Now we get into Bayes' rule, and we can just apply that to analyze the new event, calculate the probability of payoff or whatever we're looking at, depending on the problem. So you've got Bayes' rule there in red, and you can set it up accordingly with the numbers that I gave you above. One thing that I like to do is kind of just write out everything rather than doing it in my head, especially when you are taking these exams and you do have quite a bit of time. I don't remember this exam being particularly rushed at all. Then you're going to want to redo step 1. Now that we know there's only a 20% chance that the company is strong. So again, that's going to be exactly what we calculate here. We're just conditioning it based on the other information that we're given. And the expected utility, once we go back and redo step 1, knowing that the company is now strong in conditioning, the expected utility of holding can be written out like this. And again, this is just algebra. So it's going to be 1/5 your utility function of 400 plus 4/5 of the utility function of 100. And that 1/5 and 4/5 is just going to be your probability. You end up with, I guess, the expected utility of holding being 12, and then the utility of selling, you set up in a similar fashion, go about solving that as well. Now that we've calculated some of that conditioning information, and then you should be good to go. And this is going to be enough to get you through one of these payoff problems. The logic is very, very similar on all of them. I'll send these notes to you all as well, just so that you can kind of go back on your own and look it over before you go into the exam. But this is practically what I used to study, or something very similar to this. Next topic you covered was Nash Equilibrium. So basically the Nash equilibrium are the locations at which, if players are currently situated, nobody would be able to deviate towards a higher payoff. And it exists where the best response functions of all players intersect. So the column players in blue, row players in orange here, and I've kind of set it up for you. So I'm just giving you a couple of payoff matrix examples. And if you see one of these problems, I would just walk through it like this. So you have step one, write out both players' best responses for all of the other players' possible selections. So I would go about saying, oh, the best response for, L is going to be you. In response to L is going to be you for the row player. Likewise, your best response for, the column player playing you, the row player playing you is going to be the column player playing R. So write that out. You can write it out visually if you're better with that, like this. And basically you're gonna walk down and look for the intersection. So step two basically is just starring each payoff corresponding to the best responses. That includes ties as well. And then step three is going to be identifying the intersection points between the player's best responses. Those are gonna be the Nash equilibria. So you see here, some of these are just 1 star, but when you have both, that's going to be your intersection. You can circle those and that's going to be ultimately your Nash equilibria. Cournot duopoly. So I've got an example of this here, as well as the steps that I would apply to walk through it. So let's say we're given this problem, we get a market demand for X, P equals 90 minus 2X, where we kind of have that, that restriction, where we've got X equals to XB plus XH. Cost function for XB, cost function for XH will be given as well, and you're going to be able to calculate the profit functions of both firm B and firm H in terms of relative outputs. So that's right here. What I mean by that, as you can see, you've got your profit function. So that's pi I as a function of your relative outputs. We end up with xi plus x negative I multiplied by pi minus ci. That's of course going to give you this system of equations. From that, we can actually calculate the best response function for both firms. Best response is going to be denoted BR again. And you see mathematically here, depending on how complex the equation you have, you can break it out into partial derivatives, whatever you need to do. Once you've done that, we're going to be able to calculate the optimal best responses here. And then step three is, of course, going to be locating the intersection. If I'm better with visuals, so if you put it up on a graph, it also helps you a lot, or at least draw out like an estimation of it and put the formulas on. But ultimately, you're just trying to locate the intersection between the best response functions, and this is going to be your Nash equilibrium. Now, I believe the next thing you covered is mixed strategy. So that's going to look something like this, and we're going to have probabilities that are not just 50-50 or some sort of classical probability structure here. You'll see have it set up. We've got prob or P on the top for the column players' probabilities and Q for the row players. Step one is going to be assigning variables, Q and P, like I just said, to represent the probability of a certain row or column choice. Step two, you're going to want to set up the equation for both players such that their expected payoff is equal between their choices, despite relying on, the probability. Let's see if I'm actually recording audio, but besides relying on the probability of other players' choices, I'm just going to confirm that. I hope that this can hear me. Hello? Yeah, there we go. Perfect. Okay, give me a heart attack. Step three, we're going to be solving the system of equations that we've set up right here. And this is just, again, your response functions. Solve the system of equations for the probabilities Q and P. Here, both players are indifferent between their choices and have no incentive to deviate. This is going to be what we call a mixed strategy Nash equilibrium. And again, at the very end, you'll probably format and box your question like this, as you can see here. Next thing we're going to review is Bertrand product differentiation. So this is going to be kind of the dynamics regarding competition and pricing in specific markets. So I've got the basic outline here for you. So you've got your market demand for XA and XB, as well as the actual equations involving price of both goods. And then, of course, you've got your MCs there. So it's marginal cost for A, marginal cost for B, both going to be equal to 0. Step one, we're going to be calculating the profit functions of both firms A and B in terms of prices. So I've got that set up here for you. And then the next thing you're going to want to do is calculate the best response functions for both firms. So that's kind of the trend here, is that we're always going to be going back to calculating the best response functions, but depending on the competitive environment or whatever dynamic you're evaluating at the time, which should be kind of given to you in the question, you're going to want to change how you apply them. We end up with the best response function for A. That's going to be in terms of price. So we got PA star. What I mean by that is it's just the optimal price for A. And basically, as we go down, we're also going to see that you can locate the intersection again between the best response functions. And this is going to be your Nash equilibrium. So on the exam, I always kind of drew it out once I was going back over to check my work to make sure that it actually kind of made sense. Because if you made a dumb algebraic error, it'll stand out pretty fast. Now we'll move on to Bertrand price beating. So step one, again, calculate the profit functions of both firms A and firm B in terms of prices. Once we have that, we can set it up as such. I'm going to zoom in here just to make sure you can actually see it. But once we've set that up, we're going to want to, and again, this is because both firms have an incentive to lower the prices marginally and capture the entire market demand. So that tells us that Nash equilibrium must occur where the prices are equal and the profits of both firms are minimized but non-negative. So this is typically going to be where both prices are zero. And you can kind of see that drawn out here in terms of the competitive dynamics. So step three is going to involve both firms incorporating a price beating scheme in which firm A will change, price of A to be some sort of a equation like that, I guess. But all these numbers make sense. You can go through and check my work too. But if firm B announces that the price of firm B is going to be less than firm A, then of course firm B will also change their function to that. And if firm A announces the same, they're just going to continue competing. Now, if firm A's price does not equal firm B price, then the firm with the lower price gets the entire market demand. And that's what drives the entire problem here. For the reasons in step two, the only Nash equilibrium is going to be where price of good A equals price of B. And it's going to be 1, 1, where the profits of both are equal to 0. Now, there might be a Nash equilibrium where the profits of both are greater than 0. And this is going to involve, I'll walk you through it here. So basically, we're going to get the profit functions for price of A times the slope, I believe that is, of the other good. And we're going to minimize profits such that the profits of A equals the profits of B. But price of A does not equal price of B. Because again, that's how low they can go. We've got the problem walk through there. And for the sake of brevity, you can go back and look at it on your own. I've got little notes there for you. But I mean, in this example, we end up with a Nash equilibrium with positive profit for both firms. And this is going to occur at the price of A equals price of B equals 5 divided by 4. And this happens because neither firm could profitably deviate by lowering or now raising their prices given the other prices beating scheme. You also covered externalities. So we're going to see in this example, X and Y are units of steroids consumed by A and B. If X plus Y equals 0, then the probability of A equals the probability of B, both of them using is going to be 50%. Otherwise, you end up with that function. And this is another example. I believe it might be from one of his old exams, but of course you have all of those at the moment. And then your reward in this example is going to be $100. And you can see graphically how this works out, how your payoffs are. And in terms of solving it, step one, we're going to find the objective functions for each player. And this is going to be your expected payoffs. You can see them set up right there. After that, we're going to calculate the best response functions from the partial derivative of both players' expected payoffs with respect to their input. So that'll be set up like that. And the last step is we're going to be locating the intersection point between these best response functions, and this is going to be the last equilibrium. So you can see a pattern there. Whenever I had to apply one of these, I was always looking for an intersection point one way or another. If you can do it graphically, great. If you want to do that more mathematically, both work out great. So, I mean, memorize the basic differences between the different versions of competition, but you should be pretty good on this. Now we will review welfare. So basically, we're looking at classical utilitarian. I don't even know how to pronounce that one. Benthamine welfare function. This is just pulled from his notes. But basically, we're going to be evaluating a certain amount of money X, which can be allocated across 3 individuals. So we've got individuals G, J, and P, such that the amount to each is going to be less than the total amount. So that's kind of the restraint there, which is relatively trivial. Their utility functions are going to be set up like this. This is just given to you from the problem. we're going to maximize classical utilitarian welfare, we're going to set it up like this. So this is going to be just a maximization problem. I expect all of you to be able to do that because I think it was on D1 exams as well. And you definitely covered in Calc 2 if you didn't take Calc 3. But if we're going to maximize the other forms of welfare, we can allocate 1/4 xj to xg. So, you know, your utility of g as a function of xg is going to be equal to this formula. And you can continue to move down. And ultimately, once you put these formulas into some sort of graph or you imagine it in your mind, we're going to see a graph that works out to look like this. Step one is going to be setting up that maximization problem. In this case, we're simply allocating all of x to the individual with the greatest marginal utility. And then if we're working on the other form of welfare, we're going to be looking for the allocation that uses all of the available x such that all individuals have the same utility level. And we see that set up right here with this line. That's basically going to be setting x equal to 1 and calculate the allocation ratios. Step 2 for this one is going to be writing down the optimal allocation by plugging in for t. And this is ultimately the answer that we end up getting just through walking through the algebra there. Now, if we're going to be doing a Stackelberg outcome problem, it's a little bit different than Cournot and Bertrand. Stackelberg involves a leader who sets the output quantity to maximize their profits, and other firms follow by setting output given the leader's pick. So we can see here, just as an example problem, you've got the market demand, you've got your marginal cost curves, and firm is a Stackelberg leader. Step 1, you're going to be calculating the profit functions of both firms in terms of output. This is done the same way as Cournot. And again, we just have it set up there. Step 2, we're going to be using the profit function from the follower firm. So we've denoted the follower firm to firm F to get their best response function. That's just going to be taking the partial derivative. And then firm S now knows firm F's response and will factor it into their profit maximization problem. So we're going to be plugging the followers firm F's best response into the leader's profit equation and maximizing. So this is the problem that we end up with. This is going to occur where the partial derivative with respect to xf is going to be equal to 0, and you can kind of work through the maximization problem there. Maximization problem is ultimately going to yield xs star, so that's going to be your optimality, and you're going to be plugging this into the best response function of the following firm to get xf star. Then find prices. This is going to be your Stackelberg outcome. So again, you can follow through on your notes there, but it's just an example problem. I tried to write these out in a general framework that should work for most of the problems. If you can memorize kind of the mechanics behind it, you should be able to plug in a lot of cases, but of course, you want to be able to understand them in case prof throws you a curveball here. In terms of extensive form games, you can kind of see it broken down like this, but we're going to begin with backwards induction and incrementally move each player's best choice at the decision blocks upward. So you can see us moving up here, deciding which is the best choice and assuming that the player would decide rationally and then moving all the way back to the top. Second step is going to be the choice made at each block, and we're going to denote those as subgame perfection decision. These are highlighted in red and compose a subgame perfection strategy profile. Similar game, we can see the dollar auction. I believe this showed up on multiple previous exams, if not your problem set itself. In this example, we've got players A and B who bid on an object worth $3. Bidding is alternating and must increase at each node by integers. All players pay their last bid, but only the highest bidder receives the payoff. Their budget constraints are $3. So step 1, we're going to write out the extensive form where payoffs are represented as A, comma B for each player. And you're just going to walk through logically, similar to above. But the big thing here is that if you're going to use backwards induction, I mean, these problems can take up a little bit of time if you don't just do them in your head. But basically, you're going to be using backwards induction to locate the subgame perfection equilibria. And again, just another problem that I've left there for you. The fish and steel problem is another classic one from prof. In this problem, it's important to note that X is an externality imposed by the steel plant that may lessen the costs, but not significantly increase the cost for the fishery. Both firms are price takers here, but that doesn't have to be the case. So we got our cost functions set up, and we'll see both of them are a function of the other firm, and we got our prices as well. First thing we're going to want to do is maximize the profits of both firms, keeping in mind that the externality provides a third FOC. And then next, we're going to calculate the production profile if the firms were to merge and their profit functions and maximize. That's going to look like this here. Step 3, we're going to be, now that the fishery owns the right to clean waters, so that the steel plant must pay to create pollution at the per unit cost of PX. The fishery will supply X according to their maximization problem, their profit maximization problem. After plugging in price of X, so that's just going to be a unit for pollution again, in for F from the profit maximization problem of the fishery, it's going to yield a supply curve that's going to be equal to X times P of X, or X as a function of PX. The steel firm will demand X according to their, again, maximization problem, where the demand function is X as a function of PX. Locate the intersection between the supply and demand curves and fix PX here. So that's PX bar once it becomes fixed. Use this price to then maximize the profits of both firms. And we're going to want to keep in mind while doing this that the new revenue or cost is of X. So we can see how I worked through it here. Again, just general frameworks, plugging in, we're giving you numbers where I could probably pulled it from an old exam. I believe this is the last thing that we cover is going to be Vcg mechanism. So there are going to be 2 indivisible objects, A and B, that must be allocated across 3 players. We got our 3 players there, theta 1, theta 2, theta 3. And we're going to want to find the valuation that maximizes the sum of values across all players. And this is going to be what we denote, or what we refer to as the classical utilitarian welfare point. So we can see here theta squared, or excuse me, theta 2 gives the highest, whereas theta 3 values B the highest. So excuse me, theta 2 values A the highest, whereas theta 3 values B the highest. Utilitarian welfare is maximized at 13. And this allocation involves giving A to theta 2 and B to theta 3. Next, we're going to want to calculate the allocations and transfers according to the Vcg mechanism for this particular profile. And theta i's transfers, that could be any player, they're transferred by removing them from consideration. Recalculate the maximum from the original welfare maximum, where we had, theta I and his property disappeared entirely. This is going to look exactly like this. And once you set this up, this will be your final answer. We see here all the way on the far right, how the MCG dictates, which transfers are going to be which. Feel free to reach out if you have any questions. I'm going to send this in the group chat, and good luck with the final.